Okay, let's look at this example, see how we can solve this one. So, assume we have a frame look like this. And made of two parts, one horizontal, one line part. And then I have a pin here and a pin here. So, and then I have 200 pounds on this. That's a newt. Right in the center. The two. Meter. And the length of this part is 3 meter. This angle is 60. So this is a problem, and if someone asks us to, so it says how much force would be a point. So for example, assume they ask you the reaction of the solvent. So at A, I have a pin, so there's going to be two reactions. At C, I have a pin, so there's going to be two reactions. So I'm going to have 4 reactions. 2 here, in total 4. So if you look at it, I cannot solve it by the 3 equilibrium equations that are already. So in this one that it has it in detail. What we discussed last time is that okay, if it's like that, one way that we can handle is that you're going to take it apart, make it 2 separate, and then start to write the equilibrium for each part of them separately. If you look at the, in this case that I have, if I write it for the entire thing, nothing going to happen. So first of all, I will put all the unknown that I have, so that I have the AY here. I don't know the direction, I just assume AY and AX, and then CY. And CX. So these are my unknown. So now I'm going to go ahead and split it in 2 parts. So it's going to be this part, the AB, it's going to be joint B, and it's going to be BC. Then I will put all the external forces that I have. So I have 2,000 here. I have CX and CY. I have AX and AY. So these are the external forces. Anything else I have is going to be internal. So this is the A, and this is going to be the B, and this is going to be the B, and this is going to be the C. So anything I'm going to put there is internal. Again, I don't know which direction they are. I'm just going to assume it's going to be opposite of this. So you can just choose any direction you want and put it there. So in that case, I'm going to have Bx and By there. So whatever I have here, I'm going to have the opposite of that on the other end. So if this is going to the left, that means this one's going to the right. This is going down, this one's going up. Okay. And
you have both your y, you have your by and your cy both pointing upwards.
that's okay.
Oh, because the 2,000 newtons is Pearson, you know?
It will comes up negative. One of them will comes up negative. The important is that these two should be opposite. These two and these two, we just assume it. These two also we assume it. Any of them if any of them is wrong.
Yeah, I was comparing the wrong things.
Just make sure that these two are opposite. These two.
Yep.
For the B also, I can put this on the B and this on the B, but in this case, it's not going to help us with anything. If I had some external force there, then it would. I'm not going to put it there, but if I put it on the B, it's not give us any additional information. So now I have the AB and I have the BC, and I can go ahead and write the equation for each part of it. So first I will write for the AB. Can write the sigma of x0, sigma of y0, and sigma m0. So I mean the sigma of x0. So it gives you the ax minus bx is 0. Then I can write the sigma of y0. So it gives me ay minus by is 0. And then I have the sigma m. The moment about any point that I want, assume about a0. So it's going to tell me the bx as in contact property. So it's going to be bx times this distance. So how much is this distance?
360.
Okay. This distance here. This is 3 cosine 60. Correct? Yeah. And this one is 3
Sine.
60. So B, what you're writing, bx. So bx will be times 3 sine and bx 3 sine 60. And it's rotating counterclockwise, so it's positive. And then I have by times 3 cosine 60, and it is rotating clockwise, so it's going to be negative, it's going to be 0. Okay, so now I have this equation. How many unknown I have? 6. 4. Sorry. 1, 2, 3, 4. 4. I have 4 in them, so by themselves they're useless. There are 3 of them, and I have 4 unknown. Now let's come here and write it for the BC. So if I go ahead and for BC, I write here again. Same thing, sigma of x0, sigma of y0, and sigma m0. So sigma of x0 gives me that bx minus cx is 0. Sigma of y0 will tell me that by plus cy is 0. As minus 2000. tangent signal m about B or C would be 0 again. For example, about C is 0. So if I write it about C, everything will cancel out on the By has it moment and 2000. So it's going to be By times 4. It's going to be clockwise, so it's going to be negative. And then you have 2000 times 2. So 2000 times 2, so I'm writing the moment about the C, so 2000 times 2, and it's rotating counterclockwise, so it's going to be positive 0. So now I have 6 equations, 6 unknown. And by solving them simultaneous, this one is in a form that is not easy to do, so you have to solve this simultaneously. Yes?
Well, like the By times 4 plus the 2000 times 2, could we not solve for By right there then? Since 2000 is,
Yes.
so once we have By, we can then solve for basically everything else.
You can get the By from here, and you get the Cy from there.
Yep.
And then you look to see if you have the Cy, is it going to help you to get.
But once you have the By, you can then use that in the moment of the, or you can use it in other moments.
There, and put it here, get the Px there. Eventually, so yeah, you can solve them simultaneously, or just substitute one in another one in another, you get all of them. So if I have them right, all of them, eventually I have to get the so it has a Px. So eventually, if I'm not going to get this, Bx should comes up as 577, By as 1000, Cx as 577, Cy as 1000. And we don't have Ax and Ay here. Probably can't get them. Ax and Ay is equal to
Bx and By.
Ax and B1 from these two equations. This is also the Ax. So this is how you the regular way of solving that. There's an easier way to solve this problem. I remember when last time when I was talking about is that when you have the problem like this, look for two force members. So do we have two force members here? So if you look at that AB, all the force at the AB either is at A or at B. There's nothing in the middle. The BC is not, because you have that 2016 right in the middle of it. So if I have the two force member, what does it mean? Remember that? What does it mean if I have two force members? So I'm going to redraw them again. So force member.
So the forces on that have to cancel out basically. There's two of them, and it's either compression or tension. Their things share a line of action.
That's it. So that the force should be aligned with the member that goes from that 2 points. The force should pass through those 2 points. So here, if I want to solve it, instead of going ahead and say I have ax and ay and bx and by, I know that the forces that I have is going, so I'm going to just put, that's the 2000 there, and that's the cx there, and that's the cy there. And here, I know that whatever is that, it's going to be along that. Instead of having two, I only have one. And whatever happened here, the opposite should happen here. And whatever happened here, the opposite of that happened. So now I can go ahead and say, okay, this is the FAB, this is the FAB, and this is the FAB, and this angle is 60. Now if you want to solve that, how do you do that?
You set 3 equations for BC.
I can get set. I don't need to do anything with the AB. I can get all the equation I want on the BC. So here, just remember that this FAB here is basically equal to AX plus AY. If I calculate this and get the AX and AY and find the vector, it's going to be exactly that FAB. So now that I have I just can go ahead and say for the BC. So if I find this, so this is going to be FAB sine 60. This is going to be FAB. Sorry, that's sine 60. Otherwise, cosine. And then I can go ahead and write my Newton equation. So if I write it, sigma fx0 gives me FAB sine 60 minus cx is 0. If I write the sigma fy is 0, tells me that FAB sine 60 plus cy minus 2000 is 0, and if I write the sigma m, let's say what b, or and write it about it just to make it similar to that one I was writing about c. 0. So if I write it for there, that's the same thing as I'm going to. So I'm going to get the FAB sine 60 times 4, and then I have 2000 times 2 and 0. So the 2000 counterclockwise, and then is clockwise. And from there, I can get the FAB and CY as 6. So, if you look at it here, it's not gonna, if you miss the true force member, it's not gonna, you'll get the correct answer, it's just more work you should do. If you find it right away that you have a true force member, it will make it easier that you can solve it with a simpler solution. So that's the second exercise. Any question? So let's look at one more example and then we'll move to the next chapter. So let's look at one more example. So assume again we have a beam, two parts, so it goes like this, have the beam go like this, and the second part is this, like that. They're pinned together at that point. A, C, and there are external forces applying on that one. A single force of 10 kilonewtons. And then have the distributed load. Working in Newton per meter. And this distance is 2 to 2. So, if you have this, you are asked to find the reaction of the supports. So look at it again. I'm gonna have 3 reactions at A, 1 reaction at C, so I'm gonna end up again with 4 reactions. So, like the previous one, again, I cannot do anything with that. So if I go ahead and just put the reaction here, I'm gonna have the AX, AY, I have the moment there. I'm just going to call it M1, just in, I don't want to write M8, so I don't want you to get confused that it's a moment about 8. So it's not moment about 8, it's a moment at that sort. And then I have CY here. So I have to go ahead and again split it into parts, so it's going to be the AB, and it's going to be there, so it's going to be here, and it's going to be there. BC. So, A, B, and C. And then I'm going to just put forces. So first of all, the external forces, so I have the AX, AY, M1, have is 10 Newton. And here at BC, I have CY, and I have to replace the distributed load with a single load. Remember, when we want to replace the distributed load with a single load, 2 things we should find: its magnitude, its location. The magnitude was the area of that, whatever shape we have. So the area is 4, so it's the height times the length, so it's the 2 times 4. And the location is going to be at the centroid of that shape. So if the centroid is there, it's going to pass through that centroid. So it's going to be right in the center here, passing through that centroid. And the magnitude of that is 4 kilonewton times 2. It's going to be 8 kilonewton. Right? Now I have to go and put the internal forces there. I'm just going to follow what the rule which is here, but don't need to put it exactly that. Bx by y, so as you want to have this, and bx, by, and whatever I put on this side, I'm going to put the opposite of that on the other side, so by down. Then the opposite of that, going to be on the others, bx, by. So now if I look at the unknown that I have, 1, 2, 3, 4, 5, 6. I have 6 unknown. So to work with that, first of all, I have to find this component of that, the y and x component of this. So if I consider that alpha, that position alpha, cosine alpha, if it's the alpha, it's going to be 3 over 5, and sine alpha is going to be 4 over 5. Okay? So I can write as it's going to be, it's going to be 10 kilonewton times cosine alpha. It's going to be 10 times 3 over 5. And this one is going to be 10 times sine alpha. It's going to be 10 times 4 over 5. The rest is relatively easy. So for BC or AB, sigma x0 so kx plus bx minus 10,000 times 3 over 5 will be 0. Sigma fy is 0. So ay minus by minus 10,000 times 4 over 5, which is 0. And the next one can write the moment, again can write the moment about any point. That I want. Write it about A or B. So if I write it about A, and about A, anti-clockwise positive. So it's going to be By, if I write it down here, the By times 6. Rotating clockwise, so it's going to be negative.
E4.
That's 4. So the By, then I have this 10,000 on 4 over 5. This one's going to be times 2. And this one is also negative. Minus m1, 0. Is everything there? Anything else? Ax doesn't have, ay doesn't have, bx doesn't have, this does not have, so it's going to be only these and these and this, right? For BC, if I write a sigma of x0 for the BC, it gives me basically the bx is 0. Then sigma m about b, I write a sigma m about for b, what I have is that cy times 2 cy times 2 and it's going to be positive, and then I have 8,000 times 1 negative, and we see. So gives you the CY, which, where is the CY? 4,000. And then sigma Fy is 0. And it's going to give me By plus Cy minus 8,000, 0. So I know that the Cy is 4,000, so By would become 4,000. And you can substitute them here, find the AX, AY. And so if you do that, eventually we'll get the AX also. AY and MY, AX will be 6,000, AY 12,000, and 32,000. So sometimes when you write the equation, you might see that, okay, it's much easier to start from BC and go to the AB. If you can see that, you can, for example, here, start from the BC, find some unknown, and then go to the AB. If you don't see which one you should start first, just start all the equation, and then you can figure out that which way you want to solve it. Is there any question? So I'm going to stop for the frame here and move to next chapter.
What page, Professor? Or is that just chapter 7?
Chapter 7, 325. So from here, that we start this chapter and chapter. There's one chapter for the friction. Except for that one, everything else will go through. they're going to be extremely useful in the strength of material. So we're almost going to use everything I'm teaching from now on, use a lot in the strength of material. There's some other courses that you take. So the first thing is the internal force. Up to here, when we have as statics, it was, okay, we have some external force, I have some support, I want to make sure that object doesn't move. That's what we did. We thought we did with the frame, with the truss, with the simple beam, we put all the external forces on that, and then said, okay, now let's find out how much reaction I should have in support of that object would be in equilibrium. Now assume the object is in equilibrium. This chapter we want to see what happened inside that object that is in equilibrium. We want to look into that. So the first is that assume we have a beam like this. And there are two forces applying on that, E1 and E2. That's going to be point, that's the A. And that end is C. Assume I want to go ahead and cut this at some point and split it in two halves. So I will go ahead, so I'll go ahead at this point, point B, I cut that, I split it in two. So if I do that, what I'm going to get is the AB part and then the BC part. So I have the AB and then I have the BC. That's going to be P1 here, P2 here. The other external forces I have are AX, AY, and assume again, I will call it M1. I don't want to be confused with the M at one point A. So these are all the external forces I have. Right? Now let's go and look at the internal part. What forces I can have for the internal part of that object if I cut it?
Tension or compression.
Tension or compression. So tension or compression is going to be,
Those are going to be forces. Like
they're going to be along the
line of action.
member.
Line of action.
So the tension, if it was the tension or compression, it should be along the member. So the first thing that I have is going to be the forces that wants to, as you said, either pull it apart or compress it. And usually it calls it N. What else?
We need the moment. Like in a rotation of it.
We need what? Look at that one says, so the end, make it compressed or along. Okay. What other things can happen to them? can bend. So one way is that pulling or pushing, one way is bending. So the next internal force that's going to be, it can be there, is bending. So there's a bending moment. What else?
The shearing thing.
Like, it's correct. So like, when you cut the butter,
Yeah, I'm just trying to think of the different forces I know.
so basically you have the force that wants to cut it in a half. But you can have the force that's going to cut it in half as V or V.
Does that V stand for anything?
No, usually they show it like that. No, these forces that I have, that V, N, and M, are they going to be, are they changing if I cut another position, if I cut another section, or they're going to be constant? So,
Could be constant.
it depends. They might be, if I cut another position, they might be. If I cut another position, they might not be, they might be different. So because of that, usually you name them, you say that this is at point B, 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 and this is at point B. And called normal. Normal force. So whenever the comma said you have a normal force of x, y, z, it means that it is along the member. It's either compressing or pulling it apart. V is shear force. Means that when it's a shear force, it means that that force wants to cut that member in half. It wants to cut it like this. It's going to be like that. And M is bending moment. So basically it wants to bend it.
Are those all in newtons?
All of what?
Like with the units of measurement for those, like SI be newtons?
If your external force is SI, then you are SI. If your external force are in pounds, you are going to be in pounds and pound foot. Depend on what's your external force.
What's torsional movement? Oh, that's not.
So here, when I want to solve that, so for the procedure, usually this is the steps that you are going through. The steps. So the first step, write equilibrium equation for entire object, or AC I would say, and find AX, AY, and NY. So first of all, that's usually the first step, find the reaction of the support. Okay, so consider the entire object, write it, and find the reaction of the support. Then, for AB, sigma fx is 0, then it gives you the magnitude for the A. Usually it's going to be like that. For AB, write sigma fy is 0, and it will give you the shear. And again for AB, write the sigma m. Usually we write the sigma m at the section where we cut it. So usually we write it about the m, so the normal and v's, they don't have any moment. But if you already know the normal and v, you can write it about any other points. But when it gives you the m. So you and v, v, and so this is usually the procedure that we are using it for finding. There are 2 points here that I want. So first, we can write this equation for BC point, BC section as well. So instead of writing for AB, we could have written for BC. Sometimes it's easier to write it for left half, sometimes it's easier to write it for the right half. Doesn't matter. Okay? So look at the problem, see which half is easier to solve. And the second point that I want to mention is that do not touch the distributed load until you cut the beam or object in half. Because sometimes your cutting line is going to be in the middle of the distributed load. So if you before cutting it you replace it with a single load, then it's going to give you a wrong answer. Because part of that distributed load is going to be on one half, the other part is going to be on the other half. So don't touch the distributed load until you actually cut it. So not touch distributed load until after you split the beam. If the entire distributed load is going to be on one half, that's good. But if part of that distributed load is going to be on one half and the other part is going to be on other half, then it's going to make it a little bit complicated. Just make sure you don't touch it. Make it and split it, and then do whatever you want to do with the distributed load. Very quickly, I'm going to just show you. So it's a 2D, and the rest of this chapter, what we are doing is going to be 2D. but later on in strength of material, part of the 3D one we are gonna use. So I'm going to very quickly just tell you about the internal force in 3D. So if I have an object like this, and then I'll go ahead and have a 3D axis there. That's going to be x, y. So if I have something like that, so the normal forces is the forces that wants to either compress it or as a tension force, correct? So it's going to be like that. I'm going to have the normal forces along the y-axis. It's along the member. It's either compress it or as a tension, what elongate it, okay? The next one is the shear forces. So look at here. If this is the case, I can cut it like this, or I can cut it like this. Any other way that I can cut it? No. Either I can come from up, down, or left, right.
Does diagonal count for anything in this?
I can just find a component in these two directions.
Gotcha.
So I'm going to have two shear forces that is going to be either in the x direction, so like that, so like that we have there. There's going to be one here and one there. So it's the V in the x and the shear in the z direction. Now about the moment, the bending. Look at that. Yes. I can bend it like this, or I can bend it like this. So either I can bend it in this way, or I can bend it in this way. Right? So I can bend it in two ways to do that. So it's gonna be exactly that what you are have here. So this bending is about axis x, is it? So I'm gonna have a bending about x like that. Because I want to bend it like this. Also I can bend it about z. This one is like, if I bend it like this, it's going to be about z, my thumb. Any other way I can bend it? No. The only thing that left that I can do with that is I twist it. Correct? That's the torsion.
Okay.
I can twist it, and that's going to be torsion. And it's going to be about which axis? sure that these two, this is bending moment, part C. This is bending moment about X, and this is the portion on the right torsion. And the rest will also that's it. Normal. Shear. Later on, toward the end of the strength of material, we're going to look at how this torsion is going to affect the shape or the stress in the object. But for the statics, we don't touch that.